We are going to start a new unit on simple harmonic motion today. Simple harmonic motion is a precursor to waves. You guys are familiar with a wave. Sound is a wave, light is a wave, waves across water, they're all waves. And basically a wave's job is to transfer energy from one spot to another. And what we want to look at is how does a wave get started? What is a wave? What creates it? Okay? And a vibrating source is what creates a wave. And sometimes those vibrations happen at very regular, repeating motions. Okay? And that's called simple harmonic motion. There's actually a better definition than that. So consider a mass suspended by a spring. Okay? It's got two forces acting on it. It's got gravity pulling down and it's got the spring pulling up. And remember, there's a couple things we know about this. Okay, we know the force in the spring is given by kx, where k is the spring constant and x is the distance the spring is stretched. We know the force due to gravity is equal to mg, where m is the hanging mass and g is the acceleration due to gravity. Okay. Now, if you were to pull this thing down a little bit, then the spring's force gets bigger, and so it's going to pull it directly back up. And when the restoring force, the spring exerts a restoring force, trying to move this back to equilibrium, when that's directly proportional to distance, as is the case here, we have what's called simple harmonic motion. And so the spring will start to oscillate or vibrate up and down, back and forth, however you want to look at it, in a very repetitive, uniform motion. Okay, so simple harmonic motion, this occurs when the restoring force is proportional to the distance from equilibrium. And I'm not going to get too caught up in the definition, but what I am interested in is what this motion looks like and how we can predict what it's going to be. Okay, so when the restoring force is directly proportional to displacement from equilibrium, that's when we have simple harmonic motion. Now, if you think about this, this spring is going to move up and down, up and down, up and down at a very regular rate. Okay, and things that repeat are called periodic. Okay, periodic is repeating, and since this motion is repeating, it is periodic motion. Waves have a period. This motion, this vibration, will have a period. Okay, so period T is the symbol for period. I think we've talked about this before. It's the time for one complete vibration or oscillation or up and down movement. Okay, so if you think about it, the mass is going to start in the middle, it's going to come down, it's going to go back up through the middle all the way up to here and then come back down. It's this one. It's this full cycle, right? It's not just the top part, it's also the bottom part. One full cycle is the time for period, the time for one full cycle. Okay. The other thing we talk about is frequency, which is F. Okay, and this is cycles or waves or vibrations per second. Now, if you look at these definitions, this is time in seconds for one complete oscillation. This is oscillations per second, and so we have T equals 1 over F. Okay? Now we're going to do a lab today where you guys actually investigate some things that affect simple harmonic motion. Okay, and so let's take a look at that. Okay, now this is pretty straightforward little lab, but it takes a while, and I want to help you get some stuff set up. So make sure you're reading the directions step by step and everything. Okay, now spring on a ring stand, mass hanging off of it. Okay, and then it says give me a graph of what you think the Y position is going to look like. Graph the position of the hanger as a function of time. Okay, so and let this spot where it's at rest, let's call this 0. So of course this thing you're going to pull it down, it's going to go back up. So I want to know what that graph versus time looks like, what you think it looks like. Okay. Now you're going to actually hang the mass on there, and it wants the spring constant and the stretch, right? And so remember F equals kx, so you're going to have mg equals kx. You'll measure the distance it moves and you can calculate k. Then we need to get the motion detector set up to collect data. Okay, so you plug the motion detector into channel 1, and let me bring this over so we can take a look at it. Okay, guess I can't really do that. well, alright, this will work. Okay. What we're supposed to do is get everything set up so that our data is ready to collect. Okay, and first thing it says to do is plug the motion detector into the LabQuest. It's a digital sensor, so it gets plugged into the digital 1 port. Tap mode over here on the right side. Okay, and what we're going to do is we're going to change this. We want to enable triggering. Okay, so that means it's going to start data collection when a certain value is true, and the value we want to be true is we want the motion detector to be increasing across 0 meters. Okay, so we put in 0 there and we push OK. So now triggering is enabled, and then make sure the motion detector is on the track thing, and then what you're going to do is you're actually going to put the motion detector under the mass, make sure everything is motionless, so everything's in equilibrium, and then you touch the red bar and you click 0. Okay, and that tells the motion detector that 0 is where the mass starts instead of where the motion detector is at. Okay, then you're going to release the weight or drop it or whatever it says, but you're going to push collect. Well, okay, you're going to release the weight, wait for it all to smooth out, then you push collect. Okay, and it's not going to instantly start collecting data until the weight goes through that 0 point. So it's just telling the motion detector when to start data collection. Okay, now I just moved my hand in front of it, so there's not a lot to see there, but that's how you set up the motion detector to collect the data that you'd like. Okay, now let's keep going through this, make sure I have anything answered that we need to. Okay, once you have your data, it'll look like a sine wave. It'll be sinusoidal. Okay, and so you're going to go through this. This is pretty straightforward. You're going to go through and you're going to try to fit things to the curve and recognize values. Okay, so go through all that, and then basically you're just going to repeat the process a few times for a few different things. Now, part 2, if you get there today, what factors do you think might affect the frequency at which the mass oscillates? Well, there's not a whole lot going on in there. You've got a mass and you've got a spring, so it's probably those two things. Think about how changing each one of them would affect it, and then you're going to test each one of them. So that's what this part is. And basically what you're going to do is you're going to change mass or the spring. In either case, we need to know the spring constant and the mass, and then you're going to record the frequency. Now, the frequency that you get out of this is actually angular frequency, but the end of this lab discusses how we can convert that into regular frequency. Okay. All right. So good luck with the lab. Also, if your quizzes aren't done or you haven't handed those in, make sure I get those as well.